In this video, we'll explore a few more graphs of polar equations. So we'll start with a quick review, picking up where we left off in the last video, and then we'll do 2 new examples. So remember from the last video, we looked at some common polar curves, talking specifically about circles and spirals, and then the line theta equals a. So again, just remembering that first thing we got to do is we got to measure out the angle theta, plug that into our function to get r out. So r is a function of theta. So let's sketch a graph of r equals 2 plus 2 cosine theta. For this one, we'll maybe take a slightly different approach. Let's, instead of plotting points like we did previously, let's sketch a graph of r equals 2 plus 2 cosine theta in rectangular coordinates. So it's important here to note that we can think of this graph as a table of values that enables us to read at a glance the values of r that correspond to increasing values of theta. So let's do that real quick. We know what this will look like. This is just the graph of 2 cosine theta shifted up 2, which means that we should touch down at the axis at pi and increase up to 2 on either side of that. So if this is 2 pi and this is pi, then our graph will start here at 2, drop down to pi. We're somewhere in between pi over 2 and here. So we look like that. So that's the graph of 2 plus 2 cosine theta in rectangular coordinates. So now, if we think of this again as an angle, so we start at 0, kind of at the origin on the rectangular coordinate plane, quote, quote. So we start at 0, and our graph here tells us that we need to move out to 2. So we'll call this a half, 1, 1.5, 2 at 0. So then as we move along, at pi over 2, we reach 1. But in between, we're still greater. So maybe we'll plot a couple of these. We know that cosine of pi over 4 would be root 2 over 2. So 2 times root 2 over 2 would be root 2. And then 2 plus root 2 is roughly, 3.4. So the shape of this graph is kind of like a nautilus shell. You start out here, trace around and in on the top half, and then it's going to repeat itself, right? If we look back here at our rectangular coordinate graph of 2 plus 2 cosine theta, we pick up at the smallest value, 0, and then increase slowly, and then quicker and quicker and quicker, and slow down till we come back to 2. So it's going to take on the same shape in the second half as we trace around. So it'll look something like this. And this graph has a special name. This is called a cardioid because it looks like a heart. Like if we were to maybe color this in here, it kind of looks like a heart if you trace around both sides. So we call it a cardioid because it looks like a heart. So this is another technique that you can use to graph any given polar equation. We could, if it's simple, graph it in rectangular coordinates, quote, quote, but we want to use it as a way to read the r value from theta. So this would be theta, and this would be r. So let's do another one. Now we'll sketch a graph of 1 minus 2 sine theta. So let's take the same kind of approach here. So we'll plot 1 minus 2 sine theta on rectangular coordinate plane. Call that 2 pi. This is pi. So a couple things to note. So we've got a minus 2, which should tell us that our sine theta is flipped over the axis. It's going to be stretched out a bit, and then it's shifted up 1. So that will tell us that we'll be moving between a negative 1 and 3 at the most, starting at 1, because that'll be kind of midline of this graph. So we'll start at 1, drop down to negative 1 at pi over 2, back up to 1 at pi, at its maximum at 3 pi over 2, and then back down at 2 pi. So traces out like this. Okay, now for the interesting part. We're going to graph this Again, our horizontal axis here is theta, our vertical axis here is r, so our output is r. So we'll start out, theta equals 0, we get 1. At some point, we cross into 0. So as we start here at 1, we quickly trace around to 0. And then eventually we come back to -1 at pi over 2. So that puts us here, right? As we trace around to pi over 2, remember a negative r means that we go in the opposite direction of that angle. So then as we come back to pi, we hit 1 again. Something like that. So interestingly, we get this little loop kind of thing going on. As we leave theta equals pi, we start to increase. And then as we hit 3 pi over 2, we're at r equals 3. So we're there. So from pi, we increase out to 3, and then come back around to 0. So kind of cool that we have these graphs of trigonometric functions in rectangular coordinates that cross the axis. When it happens that we cross the axis here and here, we loop around through the origin in polar. So let's summarize this real quick. Some more common polar curves. So these are called limosons. So if we have something like r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta, where the orientation depends on the trigonometric function. In this particular one, we were looking at sine. Earlier, we looked at cosine, and that was kind of horizontally around the polar axis oriented. So if a is less than b, we'll have a limoson with an inner loop, like we did in the second example. If a equals b, like in the first example, we have a cardioid. If a is greater than b, we have a dimpled cardioid. You can kind of see that it dips in right there. And then if a is greater than or equal to 2b, we have a convex limoson, which starts to look more circular. In the next video, we'll take one more step further in the exploration of graphs of polar equations.